Math 1332, Chapter 2, Set Theory, Section 2.1, Introduction to Set Theory, Video 6, Finite and Infinite Sets. And again, I didn't say it the first time, but for clarity, this word is pronounced finite, not finite. It's not infinite and finite, it's infinite and finite, two long I sounds. So what is a finite set as opposed to an infinite set? I think everybody kind of has the idea of what it means for something to be infinitely large, like the set of natural numbers that we discussed at the end of the previous video. So what does it mean for something to be finitely large? Well, a set is finite if its cardinality, how many elements it has, is a whole number. It's actually a pretty straightforward definition. If you start counting its elements, and at some point you stop, you're at a whole number, and your set is finite. So for example, set A containing the numbers 1, 2, and 7. Its cardinality is 3. 3 is a whole number, it's finite. Or set B, the set of all humans who have ever lived. That's a large set. I'm not just talking about humans that are currently alive. I mean, every human that has ever been, for the sake of being well-defined, every human that has ever been born and lived outside of its mother's womb. Now, we're not going to have an argument about whether or not, well, I don't want to go down this path, but let's just say that when we say all humans who have ever lived, let's say post-birth. And again, just for the sake of being well-defined, not for the sake of having a discussion about when life begins. That's for a different class. If I can count your elements and eventually I stop counting, you're a finite set. So what does it mean for a set to be infinite? Some people say this is a cop-out definition, but a set is infinite if it is not finite. So if you're not finite, you're infinite. If when I count your elements, I don't stop counting, then you're infinite. That kind of makes sense. Examples of infinite sets, the natural numbers. And all of the special sets we saw before, the natural numbers, the whole numbers, the integers, the rational numbers, the real numbers. And not to hurt your head any, all 5 of these sets are the same size except one of them. More on that later. Here's another example of an infinite set. The set of all x's such that x is an element of the rational numbers and 0 is less than x, which is less than 1. This is called a compound inequality because it's saying two things about x. 0 is less than x, meaning that x is bigger than 0, but at the same time it's less than 1. Now there's not a lot of distance between 0 and 1, but if we're going to count all of the fractions in between, we would never stop because that's infinitely large. You can have an infinite set contained in a small chunk on the number line. Numbers are pretty dense like that. So it doesn't seem like there's a lot to discuss about what constitutes being a finite set or an infinite set. But I do want to give you an alternate definition because there's another way to think about being finite versus infinite. Actually, yeah, this definition requires something that we haven't talked about yet, but I am going to go ahead and bring in a new word with the understanding that this new word will be defined more specifically when we get to section 2.2. So, or, that's not the word. Here's an alternate definition, but in order to give that definition, I have to set up a new concept called a one-to-one correspondence. The idea of a one-to-one correspondence is pretty straightforward. You have two sets, like the set of fingers on my left hand and the set of fingers on my right hand, and you can pair them up, one element from one set with one element from the other. So for example, when I put my fingers together like this, I'm pairing up my pinkies, my ring fingers, my middle fingers, my pointer fingers, and my thumbs. This is an example of a one-to-one correspondence between the elements on my left hand and the elements on my right hand. A one-to-one correspondence is a pairing between two sets. A pairing between two sets such that every element of the first set is paired with exactly one, and there's the catch, exactly one element of the second set. So I can put my fingers on my left hand in one-to-one correspondence with my fingers on my right hand. Or I can put all of my fingers in one-to-one correspondence with all of my toes, because I have 10 of each. Let me show you an example of something that's not a one-to-one correspondence. These 4 markers, these 5 fingers. There's no way I can pair them up so that everybody is paired with exactly one element of the other. In other words, one finger is paired with exactly one marker. If I keep them one-to-one, is everybody paired up with exactly one thing from the other set? No. These 4 fingers are, but this thumb is not. Now, if I pair this thumb up with a marker, it's going to force me to have what's called a 2-to-1 correspondence. I have 2 fingers paired up with this black marker. Everybody else is 1-to-1. The reason that can't happen is because it's not the same number of elements. Now, if I had a 5th marker and this one doesn't have a magnet, then yeah, I could create that one-to-one correspondence. But in the absence of a one-to-one correspondence, I can't do that. You could also say a one-to-one correspondence means that 2 sets have the same cardinality. Just think about it. 4 markers, 5 fingers, can't pair them up one-to-one. 5 markers, 5 fingers, I can. But the reason I'm bringing in the one-to-one correspondence concept is to show you an alternate definition of an infinite set. A set is infinite if it can be put in a one-to-one correspondence with a, and here's the terminology I haven't defined yet, proper subset of itself. A subset is a set contained inside of a larger one. For example, in this set of 5 markers, the black markers are a subset of the set of markers because they are a set inside of the set. What makes a subset proper is if it does not contain all of the elements of the original set. For example, these 2 markers are a subset of these 5. These 3 proper subset. These 3 markers are a proper subset of the 5. These 4 markers are a proper subset of the 5, but all 5 of them are not a proper subset. The word proper kind of implies that it is a smaller set than the one that it's contained in. Again, we're going to get into the definition of subset, proper subset, and into much greater detail when we get into section 2.2 of this chapter. But what does this mean for a set is infinite if it can be put in a one-to-one correspondence with a proper subset of itself? Well, let me start by showing you something that is not infinite. Let's just take the numbers 1 through 5. And I asked you to give me a proper subset. Meaning, list off some of these numbers, but not all of them. Let's just say 1, 3, and 5. Worst race ever. Can we put these into one-to-one correspondence, meaning one number on top paired with one number on the bottom? Well, no. The natural correspondence is to pair 1 with itself, 3 with itself, and 5 with itself, but nobody said you had to. but we could. At this point, we're not in a one-to-one correspondence because the 2 and the 4 aren't paired with anybody. And if we force them to pair, then whoever we pair it with it's going to break the one-to-one aspect of it. Now this is 2 to 1. 2 numbers paired up with this 1 number. The reason we can't make a one-to-one correspondence is because the set wasn't infinite. Now this isn't the only proper subset, but you would have to show that you can't do it with any proper subset, but I think you get the gist that if we, give me my eraser. If we take a smaller portion of this set, we'll fail to be able to put it in one-to-one correspondence with itself. But if we take a set that's infinite, like the natural numbers, one, two, three, four, dot, 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 and we take a proper subset, let's just take the even numbers. 2, 4, 6, 8, dot, dot, dot. I think it should be pretty clear that this set is a proper subset of the first one. The even numbers are a proper subset of the natural numbers because first off, every even number is a natural number. And secondly, not all natural numbers are listed here, so it is a smaller subset. But we can still put it in one-to-one correspondence by matching every number on the top with what we get when we double it. I can pair the 1 with the 2, this 2 with that 4, this 3 with that 6, this 4 with that 8, and I continue that forever. So even though I took a smaller part of it, I can still pair it up one-to-one correspondence. Why? Because it was large enough. How large? Infinitely large. So that's an alternate definition of what it means to be an infinite set. That you can take a smaller part of it, a proper subset if you will, and still pair it off one-to-one forever, and everybody is paired with exactly one element from the other set. If you're finite, that fails to happen. Remember the markers. If I had 4 markers and 5 fingers, there's no way I can match them up one-to-one and everybody have exactly one partner. If I do this, these fingers are one-to-one, but this thumb's left out. If I pair up the thumb, then somebody is 2 to 1, 2 fingers to 1 marker. If you're finite, you can't do that. If you're infinite, you can. And that's another definition of what it means to be an infinite set.